Hi everyone, my name is Iman Behbehani and I'm so excited to be sharing my work with you today. I did a project on the circumstellar material around a red supergiant named Betelgeuse. And I did my work with two mentors, Dr. Jared Goldberg, who is here, and Dr. Tavisha Dharmawardena, who is virtual. And I am so lucky to have worked with them the past 2 years. It's been a really incredible opportunity for me, and I've learned so much. But this also would not have been possible without a lot of the people in this room. So this is reflecting back on all of you. This master's program is very collaborative, and we talk to each other about our work, and we help each other, and it's, I think, a large part of what makes this program so special. So I'm very grateful for all of you. And that also includes my family, who is here and amazing, and the people who organize this program and all the professors. Thank you all. So I'm going to start by mentioning a quote that you might have heard by Carl Sagan. The cosmos is within us. We are made of star stuff. This refers to something that's quite relevant for my work with massive stars. And thank you to Anna for mentioning how important they are and how exciting they can be. Perfect setup for me. Inside massive stars, elements are fused into heavier ones, and that's where a lot of the elements that we know come from, a lot of the organic ones. Carbon, oxygen, nitrogen, those all come from fusion in massive stars. And most of the organic materials we see are made of carbon, and most of our air is made of nitrogen, and oxygen is delivered throughout our body. All of this material that comes from massive stars is what makes our life exist in the first place. So let's take a look at some of those stars. This is the night sky. And here's a constellation. And does anybody, you can shout it out, know the name of this constellation? Orion, yes. And the hunter, it has a bow and arrow, arguably a club. And its upper left shoulder over here is a star called Betelgeuse. So Betelgeuse is a red supergiant star, and it is super large. It is around 764 times the radius of the sun, which I know as, if you're not familiar with scales like these, that might be hard to understand. So that's the same thing as 5 million football fields. It's also very massive. It's 16 to 19 times the mass of the sun. And again, might be hard to conceptualize. That's 750 octillion forward focuses. That's 27 zeros. So it's like comparing an electron to a nickel. A forward focus to a to Betelgeuse, that is. So weather on Betelgeuse, there are high winds today and every day to the scale of 9 kilometers per second, which is around 2,000 times the wind speed today in Manhattan. So you wouldn't really want to go there. It's also quite hot. Temperature is around 3,500 Kelvin, but if you go a little further out into the atmosphere, it'll cool off a little on the scale of 2,600 Kelvin, with a hot spot in the northeast. So this is also flipped. The northeast region over here is about 1,000 Kelvin hotter than the rest of it. We're able to see this because of high resolution imaging with the telescope named ALMA, which we use in this project, which I'll explain more about. Those high winds combined with something called convection and pulsation of the star results in the ejection of material and then the expulsion of it, if it reaches a high enough velocity, into the larger environment. And that material can accumulate in something called a circumstellar shell or envelope a little further out into the star. And that's to scale. I traced over our observations. And that's what we're studying today. So this circumstellar shell can show us things about the nature of mass loss on Betelgeuse, and it will also affect what happens when a Betelgeuse eventually explodes. Imagine if you throw a glass bottle onto the floor, the glass is going to go in a bunch of different directions. But if you had a ring of glass around that, it'll interact with that as the explosion propagates. So when Betelgeuse explodes, it's going to hit that circumstellar material, and that'll affect the early light curve. We are taking these observations of Betelgeuse. One is in a high resolution, the one on the left, and the one on the right is a lower resolution. When you go to really high resolutions, you sacrifice things like field of view. At this high field of view, you can't see far enough out to see the circumstellar material. But at the lower resolution on the right, you can see the circumstellar material, but you can't see the star itself as well. So this is both of them on the same scale. That was zoomed in, so you could actually see the difference on the surface. But this is what it actually looks like. So to be able to actually see only the circumstellar material, we want to take the high-resolution star, match it to the low-resolution star, and then subtract them. So we're left with just the circumstellar material. To do that, we start with something called a convolution, where we take the intensities from the high-resolution data and spread them out over a Gaussian, then reproject that into the sky, basically, of the low-resolution image, and then normalize it. Then when we subtract it, we get this. So if you think of the images I showed you of the original data, it's as if I took the low-resolution image and took the star out. So we end up with this circumstellar distribution. To the left are radial profiles of the intensity and then density of that. We calculated the density with a series of equations from one of my mentors, Dr. Darmawardana's PhD thesis, and Gordon et al. From 2014. And the distribution shows that the high resolution peaks around here, and then when we normalize it, they start to match up. And around 10 arc seconds out, you see the circumstellar material start to appear. And here's with intensity and then density. But you'll notice that my density is in units of grams per centimeter squared, which is grams per area. Densities are typically recorded in what units? Grams per unit. Anybody? Mordecai? Volume. Yes, what is volume? So at the moment, at this stage, the results are not in physical units. They're in grams per area. So we need to... We do something called an inverse Abel transform to take this 3D thing that's on a 2D space and deproject it out into the 3D space that it really is representative of. And that's with something called an inverse Abel transform. This is the deprojected result of gas and dust of Betelgeuse's circumstellar environment and the original data. The red line over here indicates 1 stellar radius out. So between 4 and around 9 stellar radii is the circumstellar material. There's a density between 10 to the negative 16 and 10 to the negative 14 grams per centimeters cubed, which is much more dispersed than something like the sun, which is 1.4 grams per centimeter cubed. We plotted over this different density distributions that would result from constant mass loss rates. And you'll notice that there's no one mass loss rate that leads to the density distribution that we see. And that means that the mass loss on Betelgeuse is just quite complex, and it's not one steady state wind that results in the distribution that we see. The convection and the pulsation and the different processes on Betelgeuse result in a chaotic mass loss that gives us the distribution that we see. There's also a relationship between the rotation axis and the angle it makes with the north celestial pole, and the same angle that we'd calculate from the rotation velocity of Betelgeuse. There's an agreement between those. So there's a possibility that the distribution we see in the circumstellar environment has to do with the rotation of Betelgeuse. So it might form as a result of, or the structure may have to do with the mass loss as Betelgeuse rotates. This study from 2016 shows polarization around Betelgeuse, and regions of higher polarization indicate a presence of dust. And there is some alignment between the bluer regions where dust is likely to be and our results. You can see that there's a general agreement with where the dust is and where the dust was predicted to be. So to connect back to how I started, I mentioned how we are made of the dust from we are made of the elements made in stars. So for those elements to actually become in us and reach us, the stars need to expel the material. And that happens with the mass loss that I'm talking about, and eventually supernovae. And like I said in the beginning, this circumstellar shell is going to impact the propagation of Betelgeuse's eventual supernova. So if we were to simulate it, we can use this density distribution that I found to see how it affects the supernova. Thank you so much. Any questions? Tim.
This was awesome, Iman. And I may have missed some of the details of the observation, but what frequency are you working at?
It's around 350 gigahertz.
Okay, and so the dust temperature and grain sizes, or like what?
I don't know off the top of my head, but the resolution that the highest resolution data can capture is 18 milliarc seconds. So it can capture different nuances in the atmosphere, like a peak in the northeast right here.
Oh yeah, and is that hotspot like persistent? Or does it must rotate around, or is it at the pole? I don't.
Yeah, so the rotation axis does kind of go along that side from the rotation axis kind of looks like this.
Okay.
But this is also likely a convection cell. So it does probably move.
Yes. Very nice talk. I wanted to ask, do you have any information about the composition of the dust in that circumstellar environment? Is it carbon rich? Is it more silicate? Do you have any information about it at all?
Yeah, that's not what we did. Like, we were just looking for the presence of dust, but I believe that other studies have found there to be a lot of silicates and carbon monoxide in the circumstellar environment. Anna?
What are the timescales for the differences in the circumstellar material to arise, and when will Betelgeuse go supernova, and how does that?
I could, a great next step for this would be to add a time dependence to this, because we can do that with the mass loss that we found. But I don't know that right now, though Betelgeuse will explode in, I believe, the next 100,000 years or so.